All right, welcome back to Oceanography. We're going to keep going through Module 5. Today we're going to talk about the Anthropocene, and then we're going to talk about climate change next week, and then we're going to speculate on what might be happening in the future of our planet. So before we get into that though, some announcements, and then just make sure that you've completed all graded work, all your discussion posts, all your homework, all the assessments, including the final exam by December 6th. Okay, so let's talk about the Anthropocene. So the Anthropocene is a new geological epoch that has been proposed, and it is not without its controversy. But before we start talking about that, let's talk a little bit about the geologic timescale. So this is a nice graphical representation of the geologic timescale. So it starts here at the bottom, Earth forming 4.6 billion years ago, give or take. So the Earth and the solar system is about 4.6 billion, billion with a B, billion years old. Then here we have the Precambrian period, where there is really only single cell life, and it really doesn't resemble the Earth of today. We talked about the Hadean, which is kind of way back here, that Hull-like period, the Archean, where it's really just single-celled blue-green cyanobacteria. And then the Proterozoic, right at the end of the Proterozoic, we start getting the first multicellular animals. That's about 541 million years ago. We transition into the Paleozoic. So the Paleozoic period, you don't need to remember these names, obviously, but Paleozoic is sometimes called the Age of Fishes. So it's when fish first appeared, lower in the section, things like trilobites, eurypterids, the sea scorpions, and then we get up into the Permian. And all of these different ages are usually defined based on major life events. So the end of the Paleozoic, the end of the age of fish, is defined by this massive mass extinction at the end of the Permian. 90-some% of species on Earth died out and went extinct. It's the largest mass extinction ever in the history of the world. The one that killed off the dinosaurs gets a lot of press, and that's the one that we talk about probably the most, but it's not the biggest. This one was massive. And since 90% of species went extinct, there was a massive change in the life on Earth. And so this marks a transition period. And so we transition into the Mesozoic, middle life. This is the age of reptiles, most famously by the end, the dinosaurs, and also marine reptiles. And then, of course, there's the Chicxulub impact right at the Cretaceous boundary. That's why the Cretaceous boundary is there. That's how we define it. It's a major mass extinction, not quite as major as the end Permian mass extinction, but it killed off all the non-avian dinosaurs, all the non-birds. And then we transition into the Cenozoic, the modern life. This is things that we would kind of start recognizing as life. We wouldn't feel entirely out of place here. And then in the Cenozoic, there's Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, Holocene. These are the epochs of the Cenozoic. The Holocene is the one that we're currently in. It started 11,700 years ago. And there's a new push to define a new epoch called the Anthropocene, which would be the age of humans. So age of fishes, age of reptiles, age of mammals, and then we would be entering into the age of humans, the Anthropocene epoch. So there's a group that controls the definitions of this geologic timescale called the International Commission on Stratigraphy, the study of these layers. And in 2016, they proposed adding the Anthropocene, and they've basically been arguing about it for 4 years since, with heavy discussion from both sides. So where did this idea kind of come from? So the movement to define the Anthropocene, the age of man, the age of humans, is kind of rooted in the environmental movement. So again, think back to the counterculture at the late 60s, the 70s, really starting to embrace the environment. One of the potential real drivers for this is we left our planet And we were able to see our planet from a new perspective from outside of our planet. So here's from the Apollo 8 spacecraft in orbit, looking down on the lunar surface and seeing the Earth kind of off in the distance. From this perspective, it becomes very clear that we're just small parts in this whole cosmic game. So it becomes a little bit more clear that it's not really us versus nature. We're part of nature, and we're all confined onto this rock hurtling through space, spaceship Earth. And also from this vantage point, we can see how everything's sort of linked together into this coherent whole. So we've talked a lot about this throughout the course, in that the lithosphere, the rock, is influenced by and influences the hydrosphere, the water, which contributes to the atmosphere, and the atmosphere influences it. The cryosphere, the ice, the biosphere, the living things, all these systems link together. They're complex and they're intertwined, and a change in one cascades down to changes in the others. And the human influence is a radical shift in the biosphere, and the Anthropocene is being defined on the basis that we are now altering all of these other things. So it's kind of interesting because we have this perspective that makes us feel very small, but yet we're trying to say that our impact is very large. So can we really impact the planet? So there's kind of this saying, like, it's so vain that humans could even think that they can impact something as large as the entire planet. So we are just one species of animal on this planet. How could we possibly impact all of these very complex linked systems that have been working together for 4.6 billion years? The Earth was here 4.6 billion years before we were. It's not going to be here 4.6 billion years after we are, but maybe about that. The sun is about halfway through its fuel. We've got about half the time left. There's also the saying, like, the climate has always changed and it always will. And so these are kind of statements that are kind of trying to diminish our impact. And is that really true, that we can't impact these processes because in the grand scheme of things, we're so insignificant? Well, it's partially true, because if we look at, so carbon dioxide is one thing that's really driving a lot of these changes. Our use of fossil fuels putting carbon dioxide into the air. If we look at natural causes, natural sources of carbon dioxide, we see that there are some very large numbers here. Photosynthesis, respiration, releasing carbon dioxide from the ocean, absorbing carbon dioxide from the ocean. You'll notice the numbers on here in gigatons of CO2 per year. These are massive numbers. They are much larger than the amount of CO2 that we are putting into the air. But what you'll notice is that they're balanced. The respiration of animals is balanced by the photosynthesis of plants. The release of CO2 from the ocean is roughly balanced by the absorption of CO2 into the ocean. And so while these numbers are large, they're mostly in balance. So think of a balance with some very large weights on both sides that are canceling each other out. If you put a pebble on one side, you're going to tip the balance, even though compared to the other weight, it's pretty small. And so that's what's happening here, is that our contribution is relatively small on a global scale, but it tips the balance. It moves it out of balance. And so we're actually accumulating a net of about 15 gigatons of carbon dioxide in the atmosphere per year. We've sort of tipped the balance. We've overwhelmed some of these natural processes, and we've tilted the scale in the favor of carbon dioxide accumulating. And again, climate change we talk about can sometimes be a controversial topic. It really kind of shouldn't be, but it is. The fact that carbon dioxide levels are raising in the atmosphere is non-debatable fact. It's measured, it's directly measured. And so carbon dioxide is going into the atmosphere, it is accumulating in the atmosphere, and the globe is warming. So again, another argument is that the Earth has always warmed, the Earth has always cooled. It's been much hotter, it's been much colder. If we go all the way back to the Cambrian, way back at the beginning of the Paleozoic, the beginning of the Age of Fishes, there's a period where Earth was very hot. Middle Devonian Earth was very hot. Right before the Permian extinction, Earth was very hot, much hotter than it is today. It's been hotter. It's also been much colder during the Ordovician glaciation, during the Carboniferous glaciation, immediately after the Cretaceous meteor impact, this kind of like nuclear winter from the impact of the asteroid. So again, it's not the magnitude. It's not that Earth is going to become warmer than it ever has been. It's probably not. It's definitely not going to be colder than it ever has been. The magnitudes are really large here, but the rates are usually pretty slow. The problem is that the rate of change now is fast. And what you'll see is that every time we have this really steep drop in geologic past, these really rapid changes in temperature, these abrupt disruptions to the carbon cycle, it results in massive mass extinctions. And that might be where we're headed. So these climate changes are mostly observed in human times. So what we see is all these natural fluctuations up and down, up and down, up and down, up and down, up and down. Holocene, the last like 12,000 years, is a relatively stable time period. It's kind of remarkably stable, and everything we think of as human civilization developed during this sort of anomalously stable period. We are used to the climate being relatively steady, relatively constant, but in the last, probably since the Industrial Revolution, the last like 200, 300 years, we started pumping carbon dioxide in the atmosphere, and the temperatures have started warming. CO2 changes in the atmospheric concentration that usually took millennia are being accomplished now in decades. And so again, it's not the levels of carbon dioxide, it's not the actual temperature, it's how quickly the change is happening. So in order to define the Anthropocene, we need to think again, these breaks in the geologic timescale are defined on major changes, major disruptions in the life on Earth. And so in order to define this as a new epoch, we need to sort of prove that something's different, that something radically changed. And so the Anthropocene Working Group is arguing that our present circumstance is different enough from the Holocene as a whole, from that relatively stable geologic time period, that we need to define something new. And like all the other geologic timescale events, it has to be recognizable in the rock record. So geologists work on the strata, the layers, the stratigraphy that stack up, oldest on the bottom, youngest on top. You need to be able to see these changes in those layers. Are there things that we can recognize from the recent industrial revolution that are going to be preserved in the rock record, so that if we died off tomorrow, if alien race landed here on Earth, they would find evidence of us being here in the rocks, in the sediments? So is there enough evidence? Well, so the way that we're trying to tackle this problem, and there's a website here that you can go for more information, they developed this kind of framework to look at our impacts to the Earth system, our impacts to all the things that kind of make our life possible. And so they assessed the impact in 9 different categories. So climate change, how quick or slow the climate is changing and to what degree. Novel entities, our creation of things that didn't exist on Earth before that might be preserved in the rock record. Ozone depletion, atmospheric aerosols, so particulates in the atmosphere. The acidification of the oceans, which we've talked about. The biogeochemical flows, so the carbon cycle, oxygen cycle, nitrate cycle, phosphate cycle, all these different biogeochemical flows. Freshwater usage, land system changes, and biosphere integrity. So there's these 9 different categories. Red means it's beyond the zone of uncertainty. It's in high risk. And so what we notice is the disruptions in these geochemical cycles and the biosphere integrity, those are in the high risk zone. We're seeing rapid extinction rates. We're seeing huge disruptions to natural mineral cycles. The yellows are kind of nearing the problem area. So like climate change is nearing a tipping point. Land system change is nearing a tipping point. We are dramatically altering our landscape. And then the other categories were either not assessed or not at high risk yet. But really this whole thing, this whole concept is throughout Earth's history, Earth has sort of been moving back and forth in this kind of narrow gutter here, bouncing back and forth from ice house to hot house, ice house to hot house, ice house to hot house. Glaciers build, glaciers melt, glaciers build, glaciers melt. If we alter the system too much, we can kind of fall off into a new gutter, a new deeper gutter that we might not be able to get out of. It's called a runaway greenhouse. We've crossed over a planetary threshold from which there's no coming back to, no coming back from, I should say. So like, for example, Venus has a runaway greenhouse. Venus was perhaps at least somewhat similar to Earth in its geologic past, but now the atmosphere is very thick. There's a massive greenhouse effect. Venus is much, much hotter than it should be. The surface is essentially unlivable. So let's look at these 9 different categories. So the first one's climate change. So the warming globe, temperatures are rising. So these are the 10 hottest years on record globally. And there are some issues with the data set, like there's some sampling issues. There's the urban heat island effect. All of these are corrected for in the data set. What we see is that all of the 10 hottest years on record they start with a 2. They're all from the 2000s. They're all in the last 20 years. You've been alive for all of these. Your lifespan spans all of the 10 hottest years on record globally. What we see, again, it used to be referred to as global warming. Now we usually like to use the word climate change because the globe as a whole is warming, but there are certain areas that are actually cooling, especially around the Antarctic. There are areas that are actually getting colder in the North Atlantic as the Gulf Stream sort of weakens. There are areas that are actually getting cooler. What we see though is most of the impact is in the Arctic, and this is one of the areas that's most sensitive to this. So the animals here rely heavily on sea ice. There's a lot of permafrost here storing methane. As that increases, melting ice, exposing darker water, there's a lot of feedbacks that can increase this warming. Another thing is that we see, as we talked about, coral bleaching is increasing as a consequence of climate change. So the climate's warming, there's no doubt about it. It's measurable. Novel entities is another thing. So new man-made materials that are introduced that are not naturally occurring. If you look at the rock record, these things are just going to kind of magically appear right along time that our modern civilization appeared. So like think about plastic bags being swept into the ocean and stored in the marine sediments. We talked about microplastics, things that are man-made, the technofossils, things that we made. So by the year 2015, we have manufactured about 5 billion tons of plastic. And as you know, plastic does not break down very quickly. So we've basically made 5 billion tons of new material that didn't exist before on Earth. That's enough to wrap the entire Earth in a layer of plastic wrap. That's a lot of plastic. And the annual plastic production is roughly equal to the biomass of all the humans. If you weighed all of the humans on Earth, we generate about that much plastic every year. And we saw the consequences of this getting into our oceans, especially with our friend, the Great Pacific Garbage Patch, with this disgusting floating mass of debris. caught up in the ocean gyres. Ozone depletion is another one. So the stratospheric ozone layer here, it's very important to life on Earth. It blocks very harmful UVC rays, UVB rays, UVA mostly gets through. These are the ones that give you sunburn. These are the very dangerous, very energetic solar rays. And our atmosphere, particularly the ozone layer, shields us from that. Before the ozone layer developed, before there was free oxygen in our atmosphere, life on the surface of the Earth would have been very difficult. Just like when we explore Mars or the moon, we would need to be sheltered in spacesuits to protect ourselves from the solar radiation. Earth's atmosphere does that for us. It's like our own personal spacesuit that we're always walking around in. What we see, though, is that it was really CFCs, chlorofluorocarbons, which were used as propellants in a lot of aerosol sprays. Those were the things that were really driving the ozone hole, and they were banned internationally in 1987. And this is actually one of the better stories from the environmental movement, is that the ozone hole is generally getting smaller. Some year it fluctuates every year. Some years it's bigger than others, but in general, the trend over time is that the ozone hole is actually shrinking now. So we can reverse these damages. We've seen evidence of that. We have recognized the problem exists, recognized the culprit, acted on it, and we haven't quite solved it yet, but we've definitely moved in the right direction. So it's not hopeless. There are things that we can do to move away from this trend that we're on, if we choose to do so. There's also aerosol loading. So aerosols are particulates in the atmosphere. They actually counteract warming. So aerosols bounce radioactivity back to space. They also can act as a blanket. So there's a little bit of a cooling from the bouncing. There's a little bit of warming from the blanket, but overall it's a net cooling effect. And so as globes warm, aerosol pollution actually helps to make us a little bit cooler, and humans account for about 10% of total aerosols released. So like exhaust from cars, industrial activity, that's about 10% of aerosols. Volcanic ash, sea salt, those are natural sources of aerosol that are about 10 times bigger. We've talked about this, but ocean acidification. So as carbon dioxide levels rise in the atmosphere, carbon dioxide levels in the ocean rise as well. Water mixes with carbon dioxide to make carbonic acid, and that lowers the pH of the oceans. They become more acidic. The drop in pH in the oceans since the Industrial Revolution has gone from 8.2 to 8.1. That doesn't sound like a big change. It's only 0.1 on the scale, but you need to bear in mind that the pH scale is logarithmic, and so this is actually a 30% increase in acidity. And the problem is that marine creatures make their shells, their tests, from calcium carbonate, and calcium carbonate dissolves more readily in more acidic waters. And so this is a pteropod with a normal, healthy, clear shell, nice smooth ridges, and this is one with a damaged shell in the lower pH acidic environment. You can see that it's kind of pitted. There are a little bit more ragged edges. There are some actual like holes forming in here, and you notice that it's very difficult for this thing to maintain the orientation that it wants in the water column. But by the year 2100, the pH is projected to be under 8. And this is going to be an absolute dramatic impact on the ocean ecosystems. And then there's the biogeochemical flows. So we've talked about this as well. Phosphate, nitrogen fertilizers, carbon from fossil fuels that normally should be locked up under the earth. We've disrupted these natural cycles, and it leads to algal blooms where there's this introduction of nutrients. So here's some runoff from a river, probably some farm fields upstream, bringing fertilizers. You see this green plume here, that's algae blooming. Again, we think like, oh, okay, well, algae is blooming life is living, that's good. But remember, these things thrive at the surface, but when they die, they sink to the bottom, they decay. That decay process uses up the oxygen, and without the oxygen in the water becomes anoxic or hypoxic, and it leads to fish kills. So the fish have no oxygen to breathe with their gills. Humans have doubled nitrogen fixation in the last decade. We have doubled the amount of nitrogen that gets fixed from the atmosphere by fertilizing, essentially, our agricultural processes. We've dramatically altered the nitrogen cycle. We've dramatically altered the phosphorus cycle. We've dramatically altered the carbon cycle. And what we've seen from the geologic past is when there are disruptions in these natural processes, these natural cycles, when there are major perturbations, it's not good. There's also changes in freshwater use. So we have dammed a lot of the major rivers on Earth, and we withdraw a lot of the groundwater for irrigation and also for drinking water. We use about 50% of accessible fresh water. So of all the accessible fresh water that we have access to, we use about 50% of it. And if you look at this graph here, we've talked about this a little earlier in the course. This is all the water on Earth. Almost all of it is salt water. Fresh water is only 2.5%. Of that 2.5%, 70% is locked up in ice, 30% is in groundwater, and only a very small percent is in surface water. And we use a massive amount of it for agriculture, we use a lot of it for industry, and we use some of it for drinking. As the climate changes, certain places get more rain, a lot of places get less rain. And so this is a map of projected water stress in 2030, only 10 years from now. Yellows are low water stress, low problems with water accessibility. There is plenty of water to go around. And the dark reds are areas where access to clean, fresh, potable, drinkable, irrigatable water is going to be a problem. And what you see is that there's vast swaths of the Earth that are in water stress. A lot of the northern parts of the Earth are not, but not a lot of people really live there. This is going to be a problem. We talked about in the 1900s, a lot of wars were fought over ideology or struggles for resources that were sort of dressed up as ideology. In the future, wars might be fought over water access. And so this is increasingly a problem. And so maybe our ability to desalinate ocean water will help. Another thing that we can record in our influence on the Earth is land system changes. So if you see the Earth from space, humans have dramatically altered that landscape. We've changed where forests are. We've changed where we've built things that you can see from space. Humans, as a group, now move more sediment than all of Earth's rivers combined. This can be referred to as anthroturbation. So we are churning up, we're turbating the sediments. We move more sediment every year than all of Earth's rivers. And 85% of forests on Earth have either been cut entirely or fragmented beyond their connected usefulness. So again, just it's pretty hard to believe the scale at which we move things around. This is one of these big bucket diggers here. You see the scale here. This is capable of moving a lot of earth. This is the deepest mine on Earth. You see some buildings there for scale. It's a massive thing. Humans are capable of very great works. We can move a lot of dirt around when we want to. We can move solid rock around when we want to. Even better at it than nature is. And then the last category is biosphere integrity. So going along those lines with the forest destruction, we've displaced and destroyed massive amounts of habitat. And species extinctions, current species extinctions, it's sort of hard to estimate, We don't know really how many species exactly there are, but we can make educated estimates of that. It's also really hard to estimate the current extinction rate, but again, we can make good estimates of it. The current species extinction is about 100 times the expected kind of background rate. So there's a question of, are we in a sixth major mass extinction? So we talked about that big Permian mass extinction. We talked about the end dinosaur mass extinction. There are 3 others that are a little bit smaller than those. But are we in the 6th one? It's a little early to say. And again, like the ozone, we kind of turned that around once we recognized the problem and worked to solve it. But species are disappearing at an alarming rate. The number of endangered species is rising. It's doubled in only the last decade. And some of this is just increased awareness and more study. But that doesn't change the fact that there's a problem. An interesting thing is that some species are affected more than others. You see amphibians are especially vulnerable. Corals are especially vulnerable. These are species that are relatively delicate. They're used to relatively tight conditions, and as conditions change, they're the ones that kind of first warn us that there's a problem. Unfortunately, the corals sort of form the basis of an entire ecosystem. So this is, not good. This is not a good trend here, but it's never too late. We can still make adjustments here. Another sort of, so that's all the categories here. Well, part of the debate here is, isn't the Anthropocene just the Holocene? So the Holocene is kind of defined by when we crossed out of that glacial threshold and we entered an interglacial as the glacier started to retreat. Isn't this just an extension of that warming trend kind of out of the glaciation? There's some more argument that we didn't just start altering the climate 250 years ago with the Industrial Revolution. As soon as we started farming, as soon as human civilization really was a thing, as soon as like organized group activity was a thing, when we started slashing and burning and farming, and especially when we started plowing, we were already impacting the environment way back. And so, yes, the Industrial Revolution marks an acceleration, but we've been impacting ever since. And so that argument would be that, okay, well, if we want to describe the Anthropocene, really it's just the Holocene. The Holocene is the age of humans. We've been impacting the environment all the way back to the beginning of the Holocene. One thing we see is that if you look at orbital parameters, if you look at the Earth's orbit, the sun's energy output, our climate currently should be cooling, and it's not. Our influence has actually sort of bent the curve upward. In many ways, that's good because it's preventing the onset of another glaciation. So during the last ice age at Oswego, there was a mile of ice above our heads here. That's not something that we want, but we also don't want to drown all the coastline as the sea levels rise because the glaciers are all melted either. And so what we see here is that under this theory, humans have kind of bent this curve and prevented this warming that should have been happening. And then the Industrial Revolution was just a step change in the curve. And then if we continue to deplete all fossil resources, that's our fate. And eventually it'll come back down if we don't make it to the runaway. So if we want to define the Anthropocene, where do we start? So again, a lot of people want to use the Industrial Revolution as the start point. Maybe you can use the start of Holocene. If you use the start of Holocene, then the Holocene essentially is the Anthropocene. But some people argue that we should start the Anthropocene period at the Industrial Revolution, which is usually recognized as 1750. It started at different times in different places, but this is kind of the start of it. Basically, the big dramatic impact here is that we moved from exploiting organic fuels. So if you wanted to burn something in your stove, you were probably burning wood. You were going to cut down trees, or you were burning whale oil in your candle. These are organic fuels. You were harvesting organic resources on the earth. So that carbon that was locked up in the tree, you've released it in the same way that it would have happened if it died and rotted. Same thing with the whale. We accelerated the process by capturing and killing it, but it would have died and gone back to the environment anyway. The real problem with the Industrial Revolution is we started exporting fossil fuels. So fossil fuels are accumulations of organic carbon that took millions of years to develop. And we started burning millions of years worth of carbon in tens of years of time. And so instead of just being part of the carbon cycle where we were just sending carbon back to the environment that would have gotten there anyways, we started using carbon that was quote unquote locked in the earth, locked in the sediments, that wasn't going to be released for potentially hundreds of millions of years. The good part about that is that it supports our modern way of life. Cheap available fossil fuels, cheap available energy, that's what we do. It provides us all of the electricity that we use. It provides us the go juice that when we turn our key in our car, it turns on and we're able to go. I don't think many people are advocating that we want to go back to living in caves or living without electricity, but there are consequences to that lifestyle. And one of these consequences is dramatically increased consumption of resources. And one of the benefits is that the population increases. We can sustain more humans comfortably. Now, there's debates about the equality of how these things are distributed, and there's very real concerns about that. But there is no doubt that with fossil fuels, we're able to support a lot more humans at a lot higher quality of living than we could before. And that's what we do. So would this be the start of the Anthropocene? Potentially, but it's not the one that they favor. So the Anthropocene Working Group is favoring 1950 because this really marks what's called the Great Acceleration. So the Industrial Revolution sort of kicked this off. And what we see on a lot of these curves here, so these are socioeconomic trends, and these are Earth system trends. What we see is that the Industrial Revolution, 1750, a lot of these things like carbon dioxide levels sort of start an upward trend at 1750, but they really take off around 1950. Same thing with nitrous oxide, so impact on the nitrogen cycle. A gradual uptick from 1970, and then a dramatic upswing at about 1950. Methane, same thing. Ozone, temperature, acidification of the oceans, again, kind of a steady upward and then a big turn. Human population follows the same trend, probably the main driver of this. Around the Industrial Revolution, population started growing at a relatively steady clip. Around 1950, it really took off. Gross domestic product, our productivity, kind of flat, starts a steady rise up, and then just this dramatic change right around 1950. Energy usage, fertilizer consumption, water usage, all shows the same trends. 1950 is when our human impact really started growing exponentially. And one of the things that we need to define the Anthropocene is we need a stratigraphic marker. We need something in the rock record that marks the start of this. At 1750, the start of the Industrial Revolution, maybe our impact is not enough to be seen. But around 1950, the dramatic increase in building large dams, moving sediments around, damming major rivers, increase in plastic production, plastics getting into the environment, plastics being stored in sediments. But the big marker is the nuclear test era. So in 1945, the Trinity test site, the first atomic bomb test, we entered the nuclear age. And then throughout the next decade or so, there were a lot of nuclear tests testing the viability of these weapons. And the nuclear fallouts recorded in sediments all around the world. And it's really kind of a game changer. In 1944, World War II, there was a lot of global strife, but we were not capable of exterminating ourselves, and we were not capable of exterminating life on the planet. 1945 was kind of a big game changer when we invented the atomic bomb. When we let that nuclear genie out of the bottle, everything changed. Now we were capable of essentially completely eradicating the biosphere. Probably some things would survive and life would recover eventually, but it was just a major game changer. And so Robert Oppenheimer, one of the scientists involved, has this famous quote, "Now I am become death, destroyer of worlds." It really was a game changer, and it's never going to go back to the way that it was. And all this activity is recorded in the stratigraphy. And so that would form the basis of this. So are we in the Anthropocene? Should we define the Anthropocene? Is there enough evidence that something's radically different? That's a good comment for the discussion board, so I'm interested in your thoughts on that. What do you think about this definition of the Anthropocene? And that's all that I've got for today. Good luck with everything. Good luck with finishing up the semester. We still got 2 more lectures, and I will see you next week. Goodbye.